Good afternoon, everyone. This is Professor Keen. We have begun discussing the work of Galileo, his dialogues concerning two new sciences. In my last set of lectures, we talked about the beginning of day one, and you might recall that the first topic that Galileo is going to be discussing is the subject of the strength of materials. That is, why is it difficult to break certain things and easy to break other things? In particular, what we're going to be focusing on to start is what is the cause of the internal coherence or cohesion, that is the tendency of objects to stick together of a body, whether that body be marble or water or a copper wire. You might recall in the last lecture, the Salviati, Sagredo, and Simplicio, the three individuals who are having this discussion in Galileo's book, had talked about fibrous or filamentous materials like ropes. You might recall that ropes are comprised, for example, of strings or fibers that are only perhaps 2 or 3 feet long, and yet a rope is 100 feet long. And so how is it that a rope can hold together that is difficult to break? And the answer they arrived at is that these fibers are wound together, and when you try to pull them, it's friction acting between these fibers that prevent this rope from breaking. Now the question is, what about non-fibrous or non-filamentous substances like a block of marble? Why is that cohesive? After all, it's very difficult to break apart a piece of marble. So Galileo, in the voices of Salviati, Sagredo, and Simplicio, ask, why is this? And the answer that Galileo begins with, in the mouth of Salviati, he says there are two types of causes for the cohesion of materials. This is on page 13 of your text. And I want to talk about these two reasons. So the first reason that Galileo provides is that nature abhors a vacuum, or natura abhorret a vacua, to use the Latin phrase that he uses. And this prevents them from separating. You might think about it this way: if you have a block of stone and you try to pull it apart, in so doing, at least momentarily, one must create a gap or a space on the interior of that object. And since nature abhors a vacuum, it doesn't like a vacuum being created, that prevents that piece of rock from breaking apart. So the question is nature's abhorrence of a vacuum sufficient to explain the cohesion of bodies? And if it is not sufficient, then one must introduce another cause. And the second cause that Galileo brings up is that substances have some kind of perhaps viscous or gluey bonding substance which holds the component parts together. So if the nature's abhorrence of a vacuum is not sufficient, then one must appeal to some kind of internal bonding or gluey or some kind of substance holding it together. Okay, so I want to talk about both of these. So first of all, the first cause, nature abhors a vacuum. How is it, or what experimental evidence does Galileo provide that leads one to think that nature's abhorrence of a vacuum is able to account for the cohesion of bodies? Well, the first example that he gives is he talks about taking two polished, smooth pieces of marble, or we might say glass. You might think about two microscope slides, very smooth pieces of glass, or two plates of glass. And if you put these one on top of each other, you stack them, it is very easy to slide them past each other. So you can slide these very readily. So obviously they're not bound together by some kind of internal bonds between these. And yet if you try to pull them apart, it's extremely difficult to do so, to the point where if you try to lift the upper one, the one that's on top, the bottom one at every moment of time will stick to it and it will lift it as well, even if this is a very heavy piece of glass. So that's an example of this idea that somehow, even in the absence of a bonding substance or a gluey substance, there's something that's causing these two pieces of glass to hold together, and the reason that's given is because nature abhors a vacuum. Okay, before I go on there, I should probably say a few things about this phrase, nature abhors a vacuum. This is an ancient phrase that's at least goes back as far as Aristotle. So I should probably talk a bit about Aristotle's views on the vacuum, specifically why Aristotle, the ancient Greek, philosopher rejected the idea of a vacuum in nature. Okay, so why did Aristotle and then the medievals after them think that nature abhors a vacuum? Nature does not permit a vacuum to be formed. The argument went something like this. It had to do with Aristotle's theory of falling objects, and we'll come to this in a little bit later in the work of Galileo, but it's probably worthwhile bringing this up at this point because it gives us an understanding of his views on the vacuum. So what is Aristotle's theory of falling bodies? Again, this will come up in right now we're in chapter 2, it'll come up in chapter 3 about page 31. So here is how Aristotle thought about falling bodies, at least according to Galileo, how Galileo reports Aristotle's views. He says, according to Aristotle, when you drop an object, the speed of that body depends on its weight. This kind of makes sense. It seems like heavier things will fall more quickly than light things. If you drop a bowling ball, it falls more quickly than a feather. Okay, so this seems to be a common sense perspective. But Aristotle goes farther than this. He says that the speed of a falling body is proportional to its weight. That is, if you drop an object, it's going to fall with some speed, eventually it achieves some speed. And if you were to drop another object that is twice as heavy, then that would fall twice as fast. And if you were to drop an object that was 3 times as heavy, it would fall 3 times as fast. In other words, the speed of a falling object, according to Aristotle, is proportional to the weight of the object. This is something that Galileo is going to reject, but in the coming chapters. Okay, so the speed is proportional to the weight. What is the other aspect of Aristotle's theory of falling bodies? Well, Aristotle says that the speed of falling body depends on the density of the medium through which it is falling. And again, this seems somewhat like common sense, right? So if you drop a baseball in air, it's going to fall with some speed. If you drop it in water, it's going to fall more slowly. Why is that? According to Aristotle, it's because the density of water is greater than the density of air. So it doesn't merely depend on the weight of the object. The speed of the falling object depends on the density of the surrounding medium. And Aristotle goes a little further. He says not only does it depend on the density of the medium, but the speed is inversely proportional to the density. So if you were to double the density of the medium, the object would fall half as fast. If you were to triple the density of the medium, it would fall 1/3 as fast. In other words, the speed goes as 1 over the density, inversely proportional to the density. Now, this argument leads directly to Aristotle's views on a vacuum. He says, and this is Aristotle's view, if the speed of a falling object is inversely proportional to the density, then what happens as the density approaches 0? That is, as you drop an object closer and closer to dropping it in a vacuum. Well, as the density approaches 0, if the speed of the falling object is inversely proportional to the density, you'd have 1 divided by 0, and so the speed would become infinite. And since infinite speed implies instantaneous motion, and since instantaneous motion, you might think teleportation, is absurd, therefore it is not possible to have 0 density. It is not possible to have a vacuum. Again, this is Aristotle's argument. The speed of a falling object is inversely proportional to the density. If the density approaches 0, the speed becomes infinite. Infinite speed or teleportation is absurd. Therefore, one cannot have 0 density. One cannot have a vacuum. So this is one of the reasons, there were perhaps other reasons, but this is one of the reasons why Aristotle rejected the existence of a vacuum, and this is where this phrase comes, nature abhors a vacuum. It acts in such a way to prevent a vacuum. Okay, so now let's go back to the discussion of the strength of materials. So remember, the first reason why objects seem to be stuck together or objects experience cohesion is because nature abhors a vacuum. If you take the 2 glass microscope slides and try to pull them apart, there would have to be a vacuum created between them. Since nature abhors a vacuum, it prevents them from coming apart. And thinking about this a little more carefully, what happens if you were to take two glass slides, but instead of them being polished, they were rough. This is something that Galileo talks about in his text. If the surfaces are rough, then the bumpy surfaces allow air in between them already, and so it's actually very easy to pull apart two roughed up glass slides because you don't have to create a vacuum in separating them because there's already air in between them in the pores and gullies and caverns of the rough surface. Nonetheless, if you take those two rough surfaces and you lift the top one very rapidly, he mentions, just momentarily, the bottom slide will follow the top one just for a moment before falling back down. Why is that? Well, because as you try to pull them apart very rapidly, the air inside or between them, there's less air in between them than there will be a moment later as the air rushes in. And so what happens is as the air rushes in between them, then basically the bottom slide follows the top slide momentarily, and then as the air rushes in, then it falls back down. So that's the explanation that Galileo gives of those observations. Okay, so this is the perspective that Salviati presents again for Galileo in this text. Now, Sagredo jumps in at this point and starts talking about some difficulties in this explanation. So let's spend a few minutes talking about these difficulties. So Sagredo raises two difficulties that are related to the notion of cause and effect. In particular, Sagredo is worried about the temporal order or the time ordering of cause and effect. So let's talk about these two difficulties. I'm going to talk about the second difficulty first and then come back to the first difficulty. So what is this second difficulty? He says, let's go back and consider the case of two polished plates. When they're stuck together, the lower one, if you lift the top glass plate, the lower one follows the motion of the upper one at each moment in time, as was mentioned. But why does it follow it? The idea or the maxim or the rule that nature abhors a vacuum raises some problems. For the non-existent, that which does not exist, says Sagredo, cannot produce any effect. And since a vacuum doesn't exist, it cannot actually cause anything to happen. In other words, nothing cannot do something. So if a vacuum doesn't exist, it cannot be the cause of anything, namely the lifting of the lower plate. This is the first difficulty that Sagredo raises. What about this is the second difficulty that Sagredo raises. Now going back to the first difficulty, if, on the other hand, the lower plate does not follow the upper plate at each instant, then a small vacuum, so for instance, if the two plates are roughed up a little bit, if you lift the top plate and the bottom one doesn't follow it right away, a small vacuum must be, at least for a moment, created in between the plates. And the lower plate then moves upward through this vacuum a moment later so as to follow the upper plate. So if the plates are rough, then when the upper plate is lifted quickly, the small vacua are created momentarily until the air rushes in to fill them up. And again, this takes time. So what Sagredo says here then is not only is a vacuum permitted, at least momentarily, by nature, but motion of the lower plate upward through this vacuum is progressive. That is, it takes time. It is not instantaneous as Aristotle had supposed. That is, it takes time to move through a vacuum. This seems to contradict Aristotle's view that motion in or through a vacuum is instantaneous. This is, by the way, as we saw, why specifically Aristotle rejected the existence of a vacuum. It would seem to imply instantaneous motion, which was ridiculous, remember. So these are the two difficulties that Sagredo presents to Salviati regarding the explanation for the cohesion of bodies that Salviati brings up. At this point in the dialogue, what happens? He begins by answering the second difficulty of Sagredo. He says, it is true, in fact, that the smooth plates do stick together. That is, when you lift the upper plate, the lower one is lifted also. But this is not because a vacuum, says Simplicio. It's not because a vacuum is momentarily formed. It's because nature, in a sense, anticipates that the separation of the plates would imply the creation of a vacuum. And so, knowing, sort of anticipating that this would imply the existence of a vacuum, it prevents that separation from happening. This approach, or this answer that Simplicio brings up, is a very Aristotelian approach to the notion of causality. It's in fact the kind of thing that Galileo and the other moderns like Descartes and Pascal and others really want to start moving away from. Why did Descartes, Pascal, and Galileo want to move away from this kind of argument that Simplicio presents? It's because they said nature is not like a rational person. It cannot, so the moderns would argue, anticipate anything. It can't act so as to accomplish some goals, whether preventing a vacuum or minimizing work. These are some of the things that come up later. In other words, the moderns like Galileo and Pascal and so on were seeking to eliminate final causes or teleology from nature. All causality, so they would claim increasingly, must be referred to time-ordered or efficient causes. So for example, imagine you are rowing a boat. You have an oar, you're pushing it through the water. The oar pushes the water backwards, and the water moves a moment later in response to the oar. That would be an example of an efficient cause. So, and it's notice a time ordering. You've got the oar pushing the water responding by being pushed backwards. Just to emphasize the difference between appealing to these kind of efficient, time-ordered causes and the final causes or teleology that Simplicio had brought up, notice how for final causes, the concluding state precedes the earlier states. So for example, when I plan to build a house, the house exists in some sense in my mind before I even pick up a hammer or lay the foundation. So I have a final cause, a purpose of building a house. The concept of this house exists in my mind before I even start building it. According to Aristotle, nature, in a sense, exhibits this kind of final causality. Even inanimate things act in such a way as to accomplish certain ends or goals or tasks. They, in a sense, point toward that which they will accomplish. So therefore, and this brings us back to Simplicio's explanation, the lower plate rises along with the upper plate, since nature, in a sense, anticipates that their separation would create a vacuum. And since nature abhors a vacuum, they stick. That is, Simplicio would argue, one must appeal to final causes. Simplicio, and Aristotle for that matter, are okay with this idea. I want to say one more thing before I continue with the Galileo text. This plan to downplay or even eliminate final causality in favor of efficient causality, consisting of kind of time-ordered sequences of cause and effect, quickly runs into difficulty. And I want to just give two examples of how this rejection of final causality in favor of strictly efficient causality runs into some problems. The first thing is that there are some things where, well, when one thing pushes on another thing, like an oar pushing on water, it's very difficult to identify the time ordering of the events. For the moment that the oar is pushing on the water is also pushing back on the oar. One doesn't really happen prior to the other one. They are simultaneous, concurrent kinds of processes. And this is something that Newton points out about a half a century after Galileo. And this would be codified as his third law of motion. That is, for every action or force, there is an equal and opposite reaction or force. So when the oar pushes on the water simultaneously pushes back on the oar. The second thing that I want to point out is that much of modern physics, beginning about 150 or 200 years after Galileo, would explicitly make use of the notion of final causes in the formulation of physical laws. So, for example, nature acts in such a way as to, for example, maximize entropy production. Or nature acts in such a way as to conserve energy. Or later on, so as to extremize the action functional. This is a terminology that's used in some upper level physics. These are, in the end, clearly teleological kinds of statements that employ the notion of directedness, final causes, or an end-seekingness of nature. Now, how does Galileo respond to this discussion between Sagredo and Simplicio about the cause of the coherence of these glass or marble plates and its relationship to the principle that nature abhors a vacuum? Well, Galileo simply ignores the issue. Or at the very best, he sidesteps it by simply asking, if nature abhors a vacuum, then we should be able to simply measure how much she abhors a vacuum. This attention, or one might say insistence on quantitative measurement at the expense of a complete causal account, is really one of the hallmarks of modernity. It's not that the ancient or medieval thinkers could not or did not measure or design things or use mathematics and measurement to understand nature. You really only need to look at the rigorous, ingenious mathematics of somebody like Ptolemy in his Almagest, or Archimedes, the Babylonians, Fibonacci, Erasmus. The list goes on and on. The clever kinds of engineering work, shipbuilders, architects, food processing, musical instrumentations. There's a great deal of practical invention and careful experimentation in ancient and medieval times. What's really different about the moderns, beginning with the likes of Descartes and Galileo, is that they are really indifferent to causal explanations that go beyond efficient or material causes. I'll have more to say about this later on in the course, but I just want to kind of alert you to this fact at this point. So for now, let me just say that Salviati, who represents Galileo, does not so much solve the problems that Sagredo and Simplicio are debating as simply changing the subject. He really asks them to focus not on the cause of coherence, but measuring how much nature abhors a vacuum. Then he says we can simply address the question of whether the maxim that nature abhors a vacuum can really fully explain the coherence of substances like marble and copper. So let me stop there, and I'll continue this discussion next time.